Welcome back, class. So last time we learned about the inverting amplifier, and we have found that the gain of the inverting amplifier is the ratio of the feedback resistance with the input resistance. So we can design any inverting amplifier by using this gain configuration. So now we are going to study about some more types of op amps and some of their applications. So the first category in the op amp classification is an inverting amplifier with T network. Okay. So the T network basically looks like this. That now in the conventional amplifier, what we have, that you have input impedance and you have feedback network, and non-inverting is usually grounded. Okay. So here you are supplying your input. This is R1, this is R2. Okay. So usually, for example, if we want to increase the gain of the amplifier, okay, so we know that we can increase that by two ways. Okay, the one way is we increase the feedback resistance. Okay, like if we increase the feedback resistance, the gain will be increases, right? So for example, if I'm using the 10 kilo ohm, okay, if I make it, let's say 5 mega ohm, if I make it 5 mega ohm, okay, now the gain will be increased because the resistance value has been increased. Okay, or the other way is if I decrease the R1. Okay, for example, first I am using 1k, so if I make it, let's say 5 ohm, okay, then the gain will be increased. But practically using these values, okay, like using 5 mega ohm or 10 mega ohm or 5 ohm resistance in the actual practical application, it's not feasible. Okay, it's not practical that we use this much high resistance and this much very low resistance at the input. Okay, so for that cases we use the T network. Okay, so the purpose of the T network is to get more high gain with the reasonable values of the resistances. Okay, so the T network look like this, that in the feedback network, instead of having only one resistance, we have three resistance with this T network. Like you can see here, it's like a T. Okay, so we have a T network here. So how we can get high gain? Now let's have a look at that. Okay, so we can actually drive the gain of the T network, and it will comes as like this, that firstly just minus R2 R1, just like the normal, and then multiply with 1 is a constant, the ratio of R3 over R4 plus the ratio of R3 over R2. Okay, the ratio of R3 over R4 plus the ratio of R3 over R2. Okay, how we are getting this? Okay, we are getting in the similar fashion as we did drive the earlier relationships. So we can write the equations here. Okay, for example, the first equation which we can write is at this node, that this current I1 will be same as I2 because of the virtual ground here. Okay, so the I1 is equal to I2. Okay, and we know that what is I1. Okay, so I1 is the V1 divided by R1, right? V1 divided by R1, this is your I1. Okay, and what is I2? I2 is this current, so this current is 0. Here we have 0 volt, 0 minus Vx, so minus Vx. At this node we have the Vx voltage. Okay, just we define a node voltage divided by R2. Okay, the second equation which we can write at this node, Vx node. Okay, so the at this equation, so if you look at this circuit, what we can do, that this current I2 plus I4, okay, these are the incoming currents, I2 and I4 will be equal to the outgoing currents, is equal to I3. okay, I2 plus I4 incoming currents is equal to the I3. Okay, so if you just write the like I2 will be 0 minus Vx divided by R2. R4 sorry, I4 it will be 0 minus Vx divided by R4 is equal to I3. I3 will be Vx minus node voltage here. So here the node voltage is V0. V0 divided by R3. Okay, so we get two equations. So if you just do some rearrangements and solve them, okay, so you can get the final answer. And if you try to write the Vx here, okay, so Vx is basically the voltage drop across the, it could be drop across the R4 and R3 or across the R2. So the Vx is basically minus of I2 into R2. So just plug in the numbers and if we resolve, okay, so this is the given solution which is detailed step. Okay, so eventually if we just do some manipulations, what we can get this formula, okay, which is written here. Okay, so this is important. So here what we can see here now the gain of the amplifier is not only depending on this ratio R2 over R1. Okay, now it is also depending on the other resistance. Okay, ratio of the R3 over R4 one time and the ratio of R3 over R2 other time plus 1. Okay, now with the reasonable values of R3 over R4, instead of like choosing very high value or very low value of R1, we can get a high impedance. So usually in the microphone, okay, for because we need high gain, okay, in the microphone pre-amplification we usually use T network because we want to get a high gain. So this is the one application of the T network. This is the one example of the T network which we will solve in the live session inshallah. You can try, but we will solve this in live session. Okay. So far we have learned the ideal operational amplifier, and we have assumed that the open-ended differential gain of the op-amp is very high. We usually use that it's like infinity. Okay, but it could be possible that we have finite differential mode gain, not infinite. Okay, like it's not very high, it's very small. Okay, so if we have finite differential gain, okay, so we know that if we have the infinite differential gain, the gain of the inverting amplifier is minus R2 over R1. Okay, we know that. But if we have finite differential gain, then the gain will become this. Then we have this an additional parameter here. Okay, so it's 1 plus 1 over open mode differential gain multiply with 1 plus R2 over R1. Okay, so the derivation is same, just simply we have to apply the nodal equation here. Okay, at this node I1 is equal to I2, and at this node, okay, this current and this current. Just apply the nodal equations like we derive this formula and we can get this formula. Okay, so just the thing is, if we have finite differential gain, okay, so this parameter will be added. Okay, so this is actually the generalized formula. Even in this formula, if you consider that op-amp is ideal and it has infinite gain, so if you just put is equal to infinity, so 1 over infinity multiply by this, so 1 over infinity will be 0, so this will be gone. So we have minus R2 over R1 into 1 over 1, which is same. Okay, so with the finite differential gain, just this parameter is added. Okay, how we are getting this? The proof with detailed calculation is given here, so just go through it. Okay, so last time, as in first lecture, I told you that we can use the op-amp for the different practical applications. Okay, for example, if you want if you have two different voice signals and you want to add a all of them, or you have two different signals, any kind of signal, audio signal, text signal, okay, text data, whatever, okay, and you want to add them, so we can add them, okay, using the op amps. So if you want to design a summing amplifier, okay, at least amplifier which add the signals, okay, so we can use this kind of circuit. So what we are doing here, okay, so we know that our original amplifier look like this one with only one input. We are talking about the inverting case, okay, this is our only one input, R1 to R2, okay. Now you want to add more inputs, okay, so what we can do, we will add the, like this is our first input, this is our second input, we add another resistance R2 here, okay, we just add another resistance R2 here. Similarly for the third, we add another resistance here and we supply the input, and all combine to this inverting amplifier, okay, this inverting input, okay. Then we have only feedback, one feedback resistance, and that's it, okay. Now what will be the output? It's very simple. We will use the superposition theorem. Superposition theorem, like in electric circuit 1 you must have studied, that we solve the each source separately, okay, we solve the each source separately. We know that this is a virtual ground, okay, so this will be 0, so we will take each input source separately. First we take only this one, V1. So if you take only V1, okay, then what will be the output? We know that for the, if we don't have this one, so this is just like simple amplifier, so it will be minus RF over R1 times input, right? So this is just simple gain of the feedback divided by the input resistance, right? Similarly, if I take second input, then my output will be feedback minus RF. So when I take the second one, when I am taking the second one, due to the superposition theorem, these two will be gone, okay, these are basically grounded, okay. So for the second one, the output will be our feedback resistance divided by its resistance, multiply with the this input, okay. For the third one, what will happen now? These two will be gone, okay, and I have this resistance R3. So for this case, output will be minus feedback divided by the input, R3 multiply with its input, okay. So we get the outputs for each case. So the combined output will be their sum, okay. So I can write minus RF divided by R1 times V1, okay, minus RF divided by R2 times V2 minus RF divided by R3 times V3. That will be my combined output, okay, total combined output. So if I just take the negative common here, so I can write this as RF divided by R1 into V1 plus RF divided by R2 times V2 plus RF divided by R3 times V3. So what we are having here, a negative sign is just like giving us 180-degree phase shift, but you are getting the summation of the V1, V2 and V3. So this acts as a summing amplifier, okay. So it's very simple that you first just take the ratio of the each one, RF over R1 the first one, then RF over R2 second, RF over R3 the third, okay. And for example, if we assume that our resistance values are same, for example 1k 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 1k, so if you take for example 1k, so these will be cancelled out, so we can get this more simplified formula which just shows that all these three signals are being added, okay. So if you want to perform adding operations, okay, so basically this is a mathematical operation. So in the real time analog circuits, mathematical operation, okay, like addition, subtraction, like the addition particularly, for subtraction we perform using this op amp circuit, okay. example we will solve in the live session. Okay, so far we have learned about the inverting amplifier. Okay, so there is another kind of amplifier which is called non-inverting. So what is happening in non-inverting? In the inverting case, you are supplying the input here, right? And this was grounded. Okay, that was the inverting case. Now we have the non-inverting case. So the non-inverting case, what we are doing, we are supplying the input at the positive terminal and the negative terminal through resistor is grounded. Okay, through resistor is grounded. Okay, so in this case the procedure is same to get the output. There is no difference. So we know that this is a virtual ground. Okay, so now here we have the voltage of V1, right? So it means here if we have V1, at this point we also have the V1. Okay, so then just write the nodal equation that I1 is equal to I2. Simple. So what is I1 here? So this is 0 volt, 0 minus this nodal voltage V1 divided by this resistance, right? And what is I2? V1 minus V0 divided by R2, right? Just simple. That I1 is equal to I2. Or we can write this as minus V1 over R1 is equal to V1 over R2 minus V0 over R2. Okay, because V1 and V2 will be combined. Okay, so what we can do next, that we can write this equation as V0 over R2 separately like this side, and these two will be coming here, V1 over R2 plus V1 over R1. Okay, or we can write V2 is equal to R2 will be coming here. Okay, and V1 is common here, so it will become 1 over R2 plus 1 over R1. Okay, so just take the V1 common. So if you just multiply R2 inside, so this R2 and this R2 will be cancelled out. So we'll have 1 plus R2 over R1. So what is the output here? Output is the input multiplied with 1 plus R2 over R1. So the gain here is 1 plus R2 over R1. Okay, so this is a non-inverting amplifier. Okay, non-inverting amplifier. The gain of the non-inverting amplifier is 1 plus R2 over R1. So if you see here, there is no negative sign here. So for example, if you supply input voltage of 1 volt here, and let's say the gain is 5 volt, so now you will get the in phase output. Okay, 5 volt minus 5 volt, and both input and output will be in phase. Okay, so this is called non-inverting amplifier. Okay, thank you very much. We will solve the relevant example in the live session. So thank you very much for your time.